Hello, everyone. Let's get started. So, first of all, this is mainly for the residents. So I'll be essentially giving. They didn't have many of talks about neural networks before, things like that. So I'll have to give an introduction about these things before. So bear with me a few minutes. Feel free to ask questions at any point when you have them. And yeah, let's get started. So I'm Iltas, and hopefully you're here because you're interested in learning about graph neural networks. The first thing, let's talk some high-level background, machine learning in general, and we'll get to graph neural networks in 5 minutes. What's machine learning? Well, we design the model. We, the humans, design the model, and the model has parameters. The parameters are these knobs that you turn slightly left or right and change the model's behavior. The model is something you want to represent and something in the world. All the models are wrong, some are useful. So this is what machine learning hopes to do, is we design the models as humans, we learn the parameters through data. So supervised machine learning, which is the most common and most widely used and the thing that works the most. We have our model, our spherical cow, and we get the input data. We try to predict something out. Our data set is the data points which have input X and output Y, and these data points are independently come out from your population. So that we assume there is no correlation among them in most cases. What do we want to do is we have this loss function, something that measures how good or bad our predictions are. We start with our model F, we give it X, and we try to predict Y, and we judge how close our prediction F is close to Y. So that's supervised learning. One flavor, which is common in deep learning nowadays, is the following. We do the learning with gradient descent. The idea is as follows. While we have not converged, somehow we compute an estimate of the derivative of the loss over our data set, and then we update our parameters, this theta thing, based on how we're going to minimize the loss. So we gradually move to a point which is hopefully good. This is a computational method to do this, not the only one, but in any case, that's it. What do we want to hope to get out from machine learning and these modeling things? Well, we want to generalize to new previously unseen data. If we had these data points here, we don't want to have a very simple model that is underfitting. We don't want to have a very complex model that overfits exactly in our points, but doesn't model the thing we're trying to do. So that's machine learning. If you haven't had seen this before, hopefully this is good enough to get started. Other things that we're going to use, the notion of distributed vector representations. That's common in natural language processing, common in deep learning. The idea is the following. We have a set of discrete things. The one way to represent this is with local representations. We have a huge sparse vector of mostly zeros and a single one when we represent something like, let's say, a banana or a mango or a dog. This, however, has the problem that we don't know how these two things correlate or combine, and it's a very discrete representation. What happens usually in deep learning, somehow different models do different things, learn a distributed vector representation. Distributed because the meaning is distributed across the components of this vector. So maybe banana and mango share this yellowness thing, whereas the dog is somewhat different. So how do you do that? How do you learn these things? That you can compute them, you can learn them as parameters of your model. The high-level idea is you can start from these representations, the one-hot representations, multiply them with this embedding matrix, and you get these distributed vectors. And now your parameter is this E here, which is an embedding. Maybe you've heard things like word2vec or things like that. These are the distributed vector representations. They are building blocks, let's say, of the things that we are trying to get at. So how you compute them or how you learn them, it's quite wide varying ways of doing this, but you'll hear me talking about distributed vector representations a few times later today.
Typically, D is a lot smaller than V. Is that
Exactly. That's part of the point where the V is you have 10,000 elements or 10,000 words or something like that. D would be 128 or 500 or something like that. So it compresses down the space in some form. That's another way of seeing these things. So graph notation, again, for the residents, most of you don't necessarily have a computer science background. Graphs look like this. You have nodes or vertices. You can see here you have edges, which can be directed or undirected edges. These are, you can see them here. You can have many different types of edges. So here I'm coloring some edges with a different color to say this. What does this graph say? Well, in this specific one, nothing. But the main idea here is that you encode the nodes, which are elements, and the edges encode relationships among those elements. So this is the high-level thing, and you can encode quite a few things in graphs. Hopefully, if the residents have any questions about notation or graphs, let me know. Very simplified thing. There are tons, of course, of things around graphs. Okay, so we got to the point where I can start talking about graph neural networks. So the idea of graph neural networks is the following. You start with a graph, a representation of your problem. What is this graph? Where does it come from? This is a modeling decision. That's something that you decide that this graph here encodes the problem you're interested in. It could be a social network, it could be a molecule, it could be a program, it could be anything that you're interested about. So that's the first part. You, as a human, have designed a graph representation of your problem. The second thing is that for each of your nodes here, you need some information. This information is encoded in a distributed vector representation, an embedding if you wish, and this is encoded for each node. So each node gets somehow a representation. You can compute it. It could be an image, so B could be an image, so you compute it from a convolutional neural network. It could be a word, so it could be an embedding, but it could be anything that you wish it to be. So this is where we start. This is the input to a graph neural network. Now the question is, what do we want to do? Well, the idea is we start from here. This graph representation will describe for most of the rest of this hour the graph neural networks. The output here is going to be, again, the same graph, but for each node you have a vector representation. And now these vectors here are going to have information not about node A, when you had initially here, but how A belongs within the context of this graph. So you're essentially saying, given the features that I had initially here, and the structure of the graph, and the neighbors, and what the neighbors had to say or do, and what is the representation here. So you compute, a GNN computes these representations once it's trained. And then what you do is you take this representation you have of your graph, the output of the GNN, and then you can pass it to something that is specific to the task that you're trying to make. So it could be the loss or something else, but it's something that it's task specific. And we'll discuss very briefly two tasks after I explain the graph neural networks.
So these funny things attached to each vertex, they're sort of somehow meaningful to the person.
Yes.
Starting. That's not the internals of the GNN. It's a meaningful thing.
It's, well, as meaningful as a vector can be, right? It's.
But it comes from outside. It's not part of the mechanism of machine learning.
It's not part of the mechanism of graph neural networks. It could be a neural network somehow processes F, let's say an image, and the image is kind of, you get a vector out of it, which could be the features that there is an edge here, or there is a face here, or there is a wheel here, or something like that. It could be that this is a word. So you kind of have something, distribute an embedding of a word, like a natural language processing word, and things like that. So it's the GNN is transparent to what the initial representation.
Are they the same? Should I think of them as the same kind of thing? Are they the same length, for example? They look identical, you know.
They don't have to be the same length, but they are. They usually are the same length, not the same vector, of course. Otherwise, this would be an identity function. But they are a representation again. It's like a feature vector of this node A is central to this in this part, or this, if it were a variable in a program that we'll see later, this variable here acts like a counter. People accumulate things into it. Things like that are learned. We don't explicitly say or know exactly what this is. We can find by analogy in some cases, but that's all.
Do they have to be unique and identifying? So for instance, if you have the same type of nodes but with different edges, you would have the same node identifier, but the edges would make it different. As in, if I have two vectors that are identical in the same graph, I can assume that they are the same type of node.
So here,
yes,
okay. You can.
Which means if I have two the same, like they don't clash, like MD5 thing, you can assume that.
You can assume anything you want in this case, yes. So the simplest scenario here is that all these vectors are identical, and you want to learn about something about the graph itself. That's perfectly fine. Okay. There are other cases where you want to attach some information to the node.
I see.
Nick?
So I'm trying to map this diagram to kind of the first slide you showed about what machine learning is, which is, you have the model and then you have the knobs, right? So is it accurate to say that the model here, the human design part, is the structure of the graph, and then the knobs that you're learning, trying to learn the parameters for it, are the parameters, the vectors? The
human element is in here. We'll discuss this in the next slide. And also, you can think of it as a feature extraction. Right? In the, let's call it old-fashioned machine learning, you extract features. Is this red or blue? Is this small or large? So you have 0, 1 things. Instead here, you can think of it as a feature engineering. Engineer your problem into a graph.
I see.
And so this is part of what we humans do, but also like there is components in here that are human related. But the parameters, most of them are here. There might be parameters how to compute these initial vector representations.
Got it, thanks.
Yeah.
Should we assume that the graphs were perhaps different examples or variable size or not necessarily the same structure?
Yes.
And if so, okay, then how, after you get the final representation, then you have like these vectors that you would like to combine into your loss, right? So then how do you, like you have a variable size input?
We'll get there eventually.
But does the output graph have the same structure as the input graph?
Yes.
So we're not adding or removing any nodes or edges? Or
Not in the flavor of the graph neural networks we'll be explaining for the rest of the talk. In principle, you can do some of these things, but let's ignore this for all practical purposes. Yeah. Okay, so hopefully that's good enough. Graph neural networks here. Let me zoom in this box. What happens is the following. Let's take this small example here. This F node is connected, E and D connect to F through different types of edges. At some point in time, let's say, E and D have some vector representations. The same thing happens with F. Now, the idea is as following. We start from for our neighbors, and we're going to do something like computing a message. That's the analogy. The message here is essentially yet another vector. The idea is that we get a function of the input, the neighboring node, the actual current node, and the type of the edge. And with this function, which could be many things, again, that's design decisions about our model. We'll discuss a few concrete options later. We get a message, meaning, again, a vector. The same thing for this edge here. Then we summarize all the messages we received from our direct neighbors, And again, summarizing can be many different things. We combine the summarized information with the current state of the node, and we update the node. So now F, essentially what happened is it had a state at time t minus 1. At time t, now it has a new state that has information about itself and how and from its neighbors. In some way, this is combined. There are many, many different ways to combine them. We'll get to that very soon. Yes?
When you say it's just a function of both nodes and also the type of edge,
Yes.
is that encoded somehow, or is it just directed, undirected?
So no, the type of edge could be that D and F, let's say, are D is below F, and E is above F. Let's say so. It's a relationship that you encode. Again, the types of edges you have is something that you decide. It's again the modeling decision of the human.
But then it's encoded directly in the vector of the edges.
We'll discuss how and when it's encoded in a second. So let's look at a function at an equation here, which is hopefully colored in a helpful way. So prepare the messages. This is a function which might be dependent on the time step t that takes the representation of your node that you're currently trying to to predict, like F in this case. It takes the type of the edge, so this K here, and optionally the type, and the information, the state, the vector, if you wish, of your input. So you do this. You compute a message for each edge. For each edge that connects, for each node that connects to Nj. Now, I'm using this fancy operator here, mostly because I couldn't find another operator in Office. But the idea is as follows. This could be any commutative operation, any permutation invariant operation for combining the messages. It doesn't matter if D and F, the edge from D to F comes first, or the edge from E to F comes first. This is an important part of graph neural networks because they make them essentially invariant to however you may shuffle your graph. And that's an important thing. In some cases, this could be a summation. In some cases, this could be a max. In some cases, this could be something else. That's, again, a design decision of our model. Nothing beyond that, but this is a general class of operations.
But you should include all the edges.
Yes, but you include all the edges that connect.
NJ.
Yes.
This anyhow.
Yeah, and we're currently here updating only one node, of course. So we get all our neighbors, we compute a message, we summarize it, and then we take our own state, this state here, and we combine this with some function q. And we now have a new state over there. Okay, so that's the high-level thing. For each node, you can imagine we have a previous state, you get messages from your neighbors, and you update your state.
Should the edges be going from Nj to N, or did I miss something in the notation?
Depends on notation, but
under the big union?
yeah.
Yeah.
It's, I guess you want, Nj should have been here.
Yeah.
Yes. So this is the process for updating one node. How does this, most of the common graph neural networks work? Well, you have one of this, the parameters are shared across all of this for each node. And then there is a clock, very much like a CPU. At each point, a clock ticks. When it ticks, every node gets input from all its neighbors, computes its messages, updates its state. The clock ticks again, and the process repeats again and again. So how many times do you run this? That's a hyperparameter, a design decision, however you want to call it. There is no notion of convergence or other fancy things like that. But that's how a graph neural network works.
But the new computed value has to be saved separately, so you only update all of the values at the end, because otherwise the order in which you update the nodes will change.
Yes, you do this in parallel. So,
Okay.
which brings me to the next slide. You can think of this as unrolling the graph, multiple ways in time, and now each vector will get updated again and again and again. So all nodes update their states simultaneously, in parallel. Each slice here, you see all the nodes in the graph have one state.
And as time goes on, how are these f functions evolving as well? Or does that depend
By f functions, you mean?
the ones that you compute in this union?
So once you have inferred once you have trained your neural network.
We'll just show the next slide with the big.
Yeah, I'm trying to get there. Yeah. Yeah.
So these
So-
FTs, so
yeah.
are they the same across?
You can again modeling decision. You might decide that ft is a different for it's dependent on t. You might decide that q is dependent on t. In many cases they don't. In some cases they do. That's entirely up to you. But usually, in some cases, you can think of this as something that depends on the time t, but it's shared across all time slices.
So the thing you're missing out in this expression is the parameters, right? So both f and q get theta as an input as well.
Yeah, so parameters can be in f, and they
So it's
usually
really ft of theta and there's other things, and it's q of
Yes.
theta and there's other things.
yes,
There's a silent theta here.
yes, yeah, and we'll discuss. I think in 2 or 3 slides there are concrete choices that people make where the parameters will be more explicit at least. Okay, so what this means is that in the beginning, each node knows about itself. The next step, each node learns about itself. Well, we knew that already, and its neighbor one, distance one neighbors. And the next step, their neighbors have also been updated. So now each neighbor knows about itself, about its neighbors, and its neighbors' neighbors. So you increase essentially this field, perceptive field of what you know about each node. And by more time steps, hopefully you learn more about how you belong in the graph.
Is this like spanning tree protocol in networking?
I don't think so. I cannot say that I'm very familiar with that. Yeah, okay, no. Graph neural networks, you started from some state, you got the output. Now you have all these vectors here that are about information, about the node, and how it belongs in there. And now you can do anything you actually care about in your application. You can say, I want to pick one node from this graph that has some property. So you can do that. This is node selection. You can label each node. You can add add a class, for example, and you take each representation here and classify it somehow. Or you can decide to summarize all these vectors you have here and do graph classification. So there are different ways to do this. It's very application dependent. We'll discuss when we go to some applications. Okay, so let's take a very, very simple example. Not very practical, but still, it's the simplest possible you can get. So you have this age, where you got out from each node at the final time step, and you multiply it with a single layer MLP, and what you get out of it is a binary decision, a 0-1, assuming that this makes sense for your application, right? Now you have a loss, essentially, saying that the classical binary cross-entropy loss, saying that I want my decision for each node here to match my value yn, whether it's true or false, 0 or 1. What's the application? I don't know. I just made this just to make this a concrete thing. Now, what this means is that I have a loss. I can compute its gradient, and with automatic differentiation, we compute the gradient through the graph neural network, and I can update the parameters, here the W, everything in the GNN, everything in the initial layer, and this is how learning with graph neural networks would work.
So is this a step that's done, so your graph neural network produces this output, and from this output you then train a classifier based on it, or is it something that you incorporate into the graph neural network?
It's all end-to-end, right? So you can think of this as a function, the loss, for a single example at least, over the parameters of all the parameters you have in your model, and you backpropagate through to all the parameters. In most cases, it's the most common thing to do.
But in doing the backpropagation, it's over the entire stack. So it's a pretty giant expression that you're differentiating.
Yes, you wouldn't want to do the differentiation manually. That's for sure.
I think so, yeah.
Also, do you run into problems like exploding gradients and so on? Like, because this sounds like a very hard RNN problem, and RNNs are sometimes.
It depends on the architecture. Again, there are many architectures. They're coming up next. Some of them look more like GNNs, and you can think of them as a stack of CNN layers. Some of them are RNNs. Usually, the unfolding happens for 10 steps, let's say. So you never get into that big of a problem. And again, you use an RNN, which is like a GRU or something like that. So that, or you use residual layers, like in CNNs. And hopefully, you don't run into this problem in most cases.
Where's the update rule for these H states?
What do you mean? The update rule is stochastic gradient descent, or stochastic with momentum, or.
How do you compute? How do you go from HT to HT plus 1? HT.
So the HT, you mean HT is in a value in the model, right? You don't update HT. It's not a parameter. W is a parameter.
No, I get that, but okay, maybe you say it in a second.
I'm not sure what you're asking. That's
because earlier you said there would be an update rule for each of these states, for each of these H vectors.
So H here is the output H. So maybe this T should have been capital T, the final thing when you go over there.
Right. Yeah. That's what I'm. Okay.
How you update H?
Yeah. Okay. That depends on the graph neural network architecture. So let's look at two popular graph neural network architectures. So the first one is gated graph neural networks. It was first invented in this building. I wasn't here at the time. But the idea is as following. We want to compute the messages. We say that a message depends on the type of the edge, K, on the neighbor, and the state of the neighbor, D, so age of node D at time T minus 1. This is copy-paste, of course, so that's equally wrong. And it does not depend on F in this case. So here, this is E, is a parameter of the model, and you do a matrix multiplication, you transform the state, the input state of your neighbor with E. Your summarization, your permutation invariant method is just a summation. So however you order this sum, it doesn't really matter, it's a sum. Well, modulo floating point, but don't worry. And then here, you get your previous state. You have an RNN cell, a recurrent neural network. This one is called GRU, doesn't matter. It has some parameters in it. And it takes the previous state, the message that you just computed, that is summarized information, and updates its state.
What's K?
K is the type of the edge here. So you can say that the white one is 0, the red one is 1, something like that. So you have a finite and usually small set of edges.
And I guess your F depends on the type of edge you're showing?
The
function F.
The function F, yes. So that's where this is what previously we had an F as F here. So we have essentially a different matrix for each K, which is an n by n, where n is the dimensionality of H.
How come there's no bias term for EK?
For EK?
Yeah, like EK is H plus.
You could add one. It depends on your application. There are variants. We add this. I think the original GGNN doesn't add one. You can say that a bias essentially will be helpful for counting how many edges come in some place. That's one option. Okay, next. Oh, Nick.
What does the gated refer to?
Sorry,
what's the gated refer to?
The GRU, which is a gated recurrent unit. Okay. Yes. So this is an RNN that says you previous state to next state. So this goes back to you have as much exploding or imploding gradients as much as you would have for a GRU with 10 steps. So not much usually. Another variant that is the graph convolutional neural networks, and that's because they resemble convolutions, and we'll see later how this this goes. But the idea is you take the states from all your neighbors, you sum them up, you multiply them with your own state, and then a matrix multiplication and division. this model originally, at least in its original implementation, doesn't support different edge types. So you see there is no dependence on K. But again, you see a permutation invariant combination and a different way of updating your state. Okay, so the first thing I didn't discuss. So okay, these are design decisions. All of them are different modeling decisions, and there are tons of them. You can go online and find more than 100 papers that change something in this equation, but the original equation is still more or less always intact. You have a way to prepare messages, a way to summarize them, a way to update your state. So the first thing is now the following. There is one trick that I have omitted so far. So let's take, for example, node D. Node D is not connected. No incoming edges come through here. So node D has no opportunity to learn about how it belongs in the graph. So a practical trick is that you add explicitly backwards edges. So you double the type of edges you have, and for each forward edge, you add a backwards edge. And now you still have a graph. The same equations apply, but information is propagated through the whole graph. That's just a trick that exists.
Isn't this related though to the assumptions that you're making about the graph? Like, surely if you said that D has a directed edge to the rest of the graph and nothing else connects to D, then that's that's a pretty strong statement about how D relates to the rest of the things, right?
So if this is the input, so you don't want to change it, right?
You mean this? Yes, but it depends on your application. If you want to learn something about D, how it belongs in there, then information has to somehow propagate back to D. Okay. And this is what this tries to solve.
Is the edge you replicate the same type or continue?
Well, you can say it's a different type. It's the same, like if this is the left of E, this is the opposite of that.
Okay, but so like basically what you want is getting feedback, right? Can you make it like weaker or stronger, or can you like change it?
You could. People don't. But yeah, there's nothing necessarily stopping you.
Would it blow up if I just had an edge type for no edge here and just connected, basically fully connected graph, but the default was...
There are some people that do something like that, where essentially you imagine a node, a God super node here, that everything connects to that and back. It works quite well in many cases. There was a question.
No, but I thought someone had the same question earlier when you were introducing the function that prepares the message. So could you also fix this by changing that function that prepares the message to treat your forward nodes and backward nodes differently? Oh, sorry, edges.
This thing currently, I mean, the way I have written this is that you take the previous state and you update the state.
Yeah.
So you still don't do anything to the neighbors. You could imagine making this more symmetrical, but that's essentially what the backwards edges are doing.
Okay. I see. So. Okay.
Yeah. Okay, so let's go one step further. The equation is nice. How do we actually implement it in a matrix operation? Again, very background things, an adjacency matrix. If you haven't seen it, let me know. The idea is that you have nodes, you assign them some ID, and you say that node 0 is connected to node 1 and node 2. And the same thing for node 1 is connected to node 2. And node 2 does not have any outbound edges. So now imagine that we have some variable, A, B, and C, just a number for now, for each node here. Then if we multiply these two things, we get this thing. So here you can think of it very vaguely as you had A here, and now you multiplied it, and B got A. So you see that the second element is A. Whereas C here is number 2 here was connected to A and B. Well, it is connected to A to B, and you can see from the matrix multiplication that this is A plus B. So this kind of implies how message propagation will start working. And the idea is you can repeat this and create these adjacency matrices easily. It's something deterministic. So let's look at some pseudocode-like thing, right? You have a matrix for where each line is your initial vector representations at time t. This is a matrix, and here is the size, which is the number of nodes by whatever dimensionality age has. Now you want to compute the messages to be sent, so you do a multiplication by ek for each type of edge k with ht, and now you have all the messages to be sent outside from a node, possibly, not necessarily all of them. And now, in order to get the received messages, you multiply this m with your adjacency matrix A for all edge types k, and you have the messages you received. And now you can apply your update function. So this is the simple mathematical kind of form that you use. And if I wanted to use a vanilla RNN, this GRU function is essentially some matrix multiplication with ht plus w with the rt here, just to make this slightly more concrete, although not very useful. Okay. How
do the matrix shapes work out in the messages to be sent equation?
So this m.
They put b times d.
Yes, and then you have this matrix ek, which should be d times m. And then you have m, and then this is also something by m. And then here they have, you need to play around with w or the GRU input to get this work. But you can make it work. I mean, usually m and d are the same in most of our implementations, so you've seen. But in theory, there's nothing stopping us to make this different.
Can you repeat what A is in that received messages?
A should be AK to be started with, so
okay.
It's a typo. But this is the adjacency matrix for nodes of type K. So this is where this comes in, like this adjacency matrix that says that node 0 is connected to 1 and 2 and things like that.
So the K's are like a finite enumeration, like red,
Yes.
green, and blue. It's not like 4.7.
In most cases, yes. And in the cases we're seeing here, definitely, yes. Okay, so yeah, you can also, you can get this thing here. So again, doing the next step is again mostly for a very practical step, but I think it's useful for the residents. Now let's make this next step. We show the high-level equation, we show the matrix. Now let's see this as a pseudocode. First, what's ainsum? I'm going to use this. I thought it would be useful for the residents. The idea is that you express operations over matrices with that. A is of size BD, B is of size QD, and the output you want is BQ. So you express essentially this operation with this Einstein summation here. And you can do more complex things. You can vaguely think of this that you here what happens is that you erase the dimension of D, right? Or you sum over it, marginalize, whatever the word you want to use. Or here you remove some other dimension. So you remove A with this, and you can express this complex sum with a simple short notation. So how does the code look like? Well, you say my initial states are somehow given to me. Doesn't really matter. We have a number of steps that we're going to unfold our graph neural network. For each time, we compute messages for each type K, which is this message multiplication that we have here.
Works on this slide, I think. But not on the previous one. So I'm still stuck on the dimensions. ND times DM makes it N times F.
ND.
And first message is K statement. Here's that one.
Yes.
ND times DM.
DM, yes.
DM gives you the output NM.
Yes.
That makes sense for the matrix multiplication.
Yes. Also, it seems that this should have been, well, they are swapped, and this should have been indexed by k.
Yeah,
Yes.
and I think on the previous slide, the notation was slightly different.
Okay. Well, I haven't noticed. So we should fix this eventually. Anyway, so yeah, this is just the notation here, and then you have the received messages, and hopefully this also gets you there, and you get the older, you sum the received messages, and you get the GRU.
The num steps, is it the input parameter?
Yes, it should have been an input parameter, a hyperparameter, a constant. Well, for in most cases when it's a constant for all your rounds or something like that. But yes, you're right. It should have been also in the input. So this ties with this here. So hopefully this makes the graph neural network a bit more concrete. The one thing I'm not going to discuss today is this specific thing here. Here we have the adjacency matrix, which is n by n, but in Einstein summation you cannot say this. But this adjacency matrix may be very sparse, but very large. So how can you make this more efficient? That's something we can discuss at another point in time.
The shapes there also don't match, right? Should be mn times nn.
We're here.
Yeah.
And no, n. This is nn, but you cannot write that in Einstein summation. So L equals n for your purposes, but it needs to be different.
The opposite.
That's exactly why you were skipping it.
Yeah, I went. It's a part of this. Yes. So, okay, let's. I wanted to go through two applications. I think we don't have the time to, so I'll go just very briefly over one with one slide. And the idea is that molecules, for example, you have molecules and you want to predict some target quantity out of it. The idea is you can see the molecules, they look like graphs. I mean, they are graphs to some extent. And now each node is an atom. You have different types of node, like carbons or nitrogen or other kind of things. I'm not a chemist. And you have different types of edges. So some are double bonds, some are single bonds, and so on. So now the question is, can you get from your molecule up to some target equation? What you do is you take this graph, you get this, and you try to predict your quantity, your target quantity. That's very high level, but hopefully it's more concrete than before. That's one option. With the other thing, which I'm not going to discuss, is about source code, how we find bugs, but I don't think that we have sufficient time to discuss through the various design decisions. Yes?
So are you swapping atoms then, so that the colors represent different types?
No, this is taken from the paper. This is how features may be computed about. This is the same atom repeating again and again, the same graph, but the graph neural network updates the state essentially for each node, for each atom, which hopefully has information that is relevant to the target quantity you're trying to predict. Yeah?
If you have time, I think they're okay to go over it.
We can do this. Well, let's see. Okay, maybe let me go first to something to. Okay, let's talk a bit about the code-related things. So the idea is as follows: we want to find bugs. Specifically, we want to do the following task. Given a blank in a program here, we want to say which of the things in the code, which of the things in the code are actually should be placed in here. So here you have first and class. Now, this helps us find bugs. You like copy-paste, someone copy and pasted this line, but the correct thing would be first. First thing we need to do, we want to take a program and convert it to a graph. How do we do it? Well, that's a design decision. That's a feature extraction, if you wish. The idea is that we want to take things like how data flows around these things, how control flows around these things, and get there. So one possible thing I'm going to show here is tokens. Well, a very boring graph. You can parse code, so you can essentially deterministically find a tree of this, and you can add extra nodes and extra edges. Again, a graph. Let me hide these edges. and take a simpler program here, and we can also add data flow edges. So when was X last written? Well, when I just entered the loop, it was here. If I'm looping, it's itself. So we can keep repeating, adding more and more edges and more different things that we believe encode the problem we have. So by the end of the day, we have a graph. For this simple snippet, this is how our graph looks like. It's not easy necessarily to parse, but it's not an uncommon thing in programming languages.
So as a design decision, would you have all of these graphs into one, all of these edge types into one big graph and then run your model rather than have multiple graphs with different types of edges?
No, you have one graph with multiple types of edges,
right,
and you do the propagation simultaneously.
Right, because this affects, right?
Yes,
the edge types do affect each other.
Exactly.
Okay.
So we're just showing it for clarity in the picture because it will be too crowded. But yeah. Yeah.
So this is like the abstract syntactic tree of the compiler, but then the edges are problem specific.
Well, some of them are of the abstract syntax tree. Some of them are token-based things. Some of them are data flow things like that.
Okay.
So how do we go around this, around doing this thing? Well, we started with this place here, and what we do is we're going to say this whole thing, I'm showing it you here as a text, but it's a graph. I'm going to add a few extra edges or nodes, saying these two candidate nodes here. We want first, for example, to be how would data flow if first was in the slot here, or how class would be, data would flow around if class was here. And now we have a big graph. I'm not showing it all of it. And now the idea is we started from our code. We got our graph. We somehow compute initial representations. I'm glossing around that part. And now what we want is our objective. We want the output of our graph neural network to have the age of the slot node here to be as close as possible to the first and as far up as possible to the class, which is the wrong thing. Again, graph neural networks, we started somehow, we encoded our problem in the graph that was dependent on what we thought we needed at least. A graph neural network says, well, this is something information about slot, about first, about class, and now this is our objective. This is, well, not exactly this, but this is more or less our objective. We can compute a loss, we can backpropagate, learn things from there. So that's essentially a second application. And let's take this simple example where the question is, what is the variable that should be here? Well, the answer, as you would have not guessed probably, is full path. The neural network knew that in a few milliseconds once getting this graph. So that's two applications. Hopefully you see this is, graphs are very broad. You can do almost anything and represent almost everything with the graphs. But this is hopefully makes the graph neural networks somewhat more concrete. I wanted to just emphasize two special cases for graph neural networks, and this is convolutions. Imagine you have a grid, like pixels, and now you take each pixel and you create the following edges. One which is top left, top right, left, right, bottom, and so on. Different types of edges. And you do this, of course, for all nodes. This, in some formulation of a graph neural network, the graph convolutional neural network, for example, this is equivalent to convolutions. Of course, it's much more efficient to do it in the current way that convolutional neural networks work, because you can batch this computation much more efficiently than doing this thing. The other thing is deep sets. The idea is that you get a set of things. It could be a variable size set of things. In this case, it's images, for example, and you want to predict something about the set. So this set of images are people with black hair and rosy cheeks, and so on. And now you get these sets of things, and you want to predict things about them. How do you encode this problem? Well, this is essentially a set, is a graph that is fully connected. Everything is connected to everything. Again, you can do a set of graph neural network, and at the output of the graph neural network, you can predict something about the set. So these are like two extremes, if you wish, about how this, about graph neural networks and some special cases that resort to something that is more or less similar to the things we had. I had slides to talk about some more advanced GNNs. Sorry, not a lot of time for that. But again, we can play around with how messages are propagated and not do the propagation like all messages, all nodes update at all points in time. That's all. So I wanted to conclude with the following more practical, non-graph neural network things, since I expected more that the residents would be the only ones attending here. But let's talk about a few things. How would machine learning, deep learning specifically, works in practice? You have your data, and now you have to do the following steps. First, from your data, you compute some form of metadata, some information about that you get from your data that will inform how your model looks like. So, how many words in your appear in your text? How many different types of edges you have in your problem, things like that. Now, given your metadata, you can convert your data into tensors, into things that look like matrices, and encode the problem. The part of the metadata, for example, could be that the word is number 53, and the word are is number 54. So you now you can say that you can create the one-hot vectors for a specific word, for example. Once you have all your data in tensors, I mean, you can do this in a flight, doesn't matter when you do it, you can batch those tensors into small groups, into mini batches. And how you do it, usually this is a separate problem. In most cases, you just have an extra dimension, which is your batch size, and you can concatenate essentially these tensors. Then you get their mini batches, and you pass them into your machine learning model. So you get tensors go in, you get a loss. A loss is a scalar. A scalar, you can differentiate the loss, try to minimize it, propagate gradients, update your machine learning model, and repeat. So this is a very high-level thing of how, let's say, non-computer vision machine learning models work. So you have these steps of metadata, converting to tensors, and creating mini batches. The next thing is about debugging. So it's notoriously difficult to actually debug these models because they're not terribly interpretable. But the high-level, there are high-level recipes about how to do this, especially with deep learning. I'm listing some of things here. These things here. Probably you'll get access to the slides at some point. But common things are: take a small sample of your data set, try to overfit your model. If your model cannot learn even your small data set, you probably have a bug somewhere. Or try synthetic data. Encode the problem you're trying in a very synthetic problem and try to make your model actually solve it. Can it actually solve it? If not, then maybe you can find from how it fails where the problems in the code appears. There are many cases where you have optimization issues, like the stock gradient descent doesn't work as you expected. One idea is you look at the learning curves. How does your loss evolve for training or the test set? This is usually what you see. If you don't see exactly like that, something like that, not exactly, you might have a problem. It might be you see that your model is never fitting, or it's underfitting, overfitting, all these kind of things. You can monitor the gradients. Do we propagate updates? Do we update zeros with do we propagate zero information about things? That's probably indicating that something is wrong with your model. And of course, there are many other ways to do things like visualizing, doing error analysis. I had this, someone who was telling me that error analysis in machine learning is what debugging is to actual programming. And this is like, you look at the predictions of your model and you try to see where does it fail. And of course, there are many other things you can do, many things that are project specific. But I thought that since it's the first, I think, deep learning lecture you get as residents, this is a good set of suggestions. So with that, I think I am mostly out of time. There are certainly questions. Feel free to ask. And yeah, Jack.
So you have for your nodes, you come up with like a representation, but for the edges, you just have like from categories. Are there any, or do people try and find representations for edges?
Yes. And there are cases where you have metadata in edges, like a number or something like that. people do use this. You can need to modify the equations in some form to get that, but it's possible. In most cases, in most of the existing data we have, the edges are just fixed there. Or you have a 0 to 1 weight. To which extent does this edge exist or not?
Do you always need to process the entire graph? Something like a social network, is it feasible to say have a focus node and only process within a certain number of links of it?
It depends what you mean need in that sense. In many cases you don't need to, but it's very convenient because the data processing, GPUs, parallelization, all these kind of things. If you want to summarize something about a full graph, then you definitely need to do this. In some other cases, you just need to focus on something. So you can say that if we take the variable misuse example, the bug thing, you're interested in a very specific place. So you know that message propagation, the last step, far, far away, won't affect your result. You could have dropped this computation. Now, writing the code to do this and doing this faster than doing everything is a hard problem. I don't think that someone has achieved this. But
so you said that convolutions and deep sets are generalizations of graph neural networks.
Yes. Well,
special cases of graph neural networks.
To some extent, yes.
So what's the message passing pixel pixel and instance to instance in those cases?
Sorry, something has gone wrong, I think, with the. So the convolutions thing. So this is in a CNN, you multiply the state of each pixel, let's say, with something that says with the kernel. This is essentially the kernel you would have, and you update the state of that node. Forget max pooling and things like that for a moment. But you repeat this. So the edges, the weights of the edges that you use is essentially your kernel. Mm-hmm. And of course, I'm showing this in this node, but the same exact edges would appear in this node, in this node, in this node, and so on. I'm not sure I answered your question.
Okay, and the other example?
In the other example, so here you get a CNN. Each image is a vector. Now, this is the initial state of each of those things. The simplest graph neural network is one without message passing. So you sum up everything, or you do a mean pooling. Or if you want to do something more complex, then it depends on the flavor of the GNN.
The message passing is what sort of defines graph neural networks.
Yes, yeah. So here you can say that essentially for each image, let's say, you had this initial representation, and you get representations from all the other images in the set. And now you update your own representation, as in what are my commonalities as an image B with everything else. And the same thing happens with A, with C, with D. And you can keep repeating this a few steps. And then at the end of the day, hopefully each image kind of knows how it's similar or how it relates with every other image. Then you need to summarize the output of these four, in this case, or all your images, which would be an average pooling, for example, average of the vectors. It depends how also deep sets have a different formulations depending on the paper you look. So, but yeah, you can transformers, for example, are deep sets. They don't explicitly say that, and this is all to attention in some form. Okay. Cool. Okay. Thanks for coming.